Yes. So if you're just joining us, we've had a quiz, and apparently August didn't do well. Oh, that's the easy part. Okay. Moving on. All right, so that was series circuit. A series circuit is characterized by how many paths for electricity?
One.
You sure about that?
Only one.
One and only one. I was on the right page. Okay, moving on to the next one, parallel circuits. Now, as I move on, we'll back up. The thing about a series circuit is, so let's do a series circuit here. So if I was going to do it like this, I would say, okay, I've got we'll make something realistic here. We got a switch, and then we have a light, and that light is going to tell me that this motor is running, right? So I've got by the way, make your light symbols like that. They make more sense. You have a positive side, a negative side. Have a switch. If it's momentary switch, we can go like that. So I've got this light and the switch, the light and the motor. And the light is there to tell me when the motor runs, okay? So let's say this motor is a very critical piece of equipment and it runs the landing gear motor. And that's how I get my landing gear down. So I really want to know when that motor's running, all right? It's very important to me. So I've designed this circuit. And so, all right, so I'm coming in for a final. Coming in to land. I don't want to land on the belly, so I energize this switch. I have current flow comes through here, lights up the light, for just about half of a second, and then, whoops, it just burns out that light. What happens to my motor? That motor is going to die. Well, lucky thing is I've got a replacement light bulb, so while I'm on short final, trying not to crash, I get out the light bulb and I put it back in and I try it again, and guess what's going to happen? Over and over and over again. Why? Because a motor draws a lot of current and a light bulb cannot handle it. So if you think about the size of a piece of wire that it would take to run even a small 5-amp motor, that wires should be thicker than your alligator clips. Your alligator clips will handle it, you'll find out, but they get a little warm pretty quick. And so they've got to be at least that big. Is a filament in a light bulb that big? No, and that's all the current has to go through that filament. So it never works. So you can't run stuff in series. It just doesn't work. You lose one thing, you lose everything. So the only time when you can talk about running something in series is if I were in fact going to put a switch in series with the motor. Now there's a problem with doing that. And that is, this switch right here has to be then rated to handle all of that current. And if you think about how wires are run in a car or an aircraft or what makes sense, let's talk about something you're all familiar with, your car. You start your car, you put the key in and you crank it over, right? And there's a wire in there that makes the starter go. But if you were to look at the wires in your column going up to that key, they're not very big, they're pretty small. So how exactly do you get the motor to turn and work with those little itty bitty tiny wires? You got to have a relay, which is really, it's a remote control, an electrical remote control. And so some of you are getting to the point where you're going to be working with this stuff. And so I want you to kind of know what it is so you don't struggle too much. But if I want to run this motor, I have to have something that is going to handle the load. So let me see. Brush up 3. So there we go. So we need a very fat wire that is going to handle the load for this motor. Right? And that goes to a pretty big ground too. But I don't want this big old fat wire going from, how would it have to run? Like in my airplane, my battery's in the back. So I'd have to have a pretty big fat wire. It's about the size of my thumb. So it goes all the way up, and it would have to go from the battery up to my instrument panel, where I would have to have a switch the size of some sort of Frankenstein kind of, double contact, and then that wire would then go up to my starter, and that would work just fine. Well, I don't want that. So the way it's wired is I have a fat wire, goes all the way from the back of where the battery is, just because it's in the back, goes up to the firewall, and then about that far away from the battery, there's a little solenoid. Then it just jumps to the let's say on the firewall. Yeah, firewall from the starter. About that far away is a solenoid, and just jumps there. So that's how you do it. So now I've got to have something to control this big old wire. So what I would do is I need a relay. Whoops, I'll go back to wherever I was. So the relay is going to have a big old fat bar up here that can move up and down, based on an electrical coil that is going to create an electromagnet that when it's energized, it will pull this bar down. We'll make that a momentary contact. We'll pull that bar down and complete the circuit. So all I can do is push this little bar down. Okay, it's a bridge. Yeah, it drops the bridge right on there, and then all the little electrons are little cars, and they go across the motor. Sure. All right, that's all I get. So now I can control, and this can be a very small little wire right here. It doesn't take much to make an electromagnetic coil. Just a lot of windings will do it. So little wire, a lot of windings. So I got to control that. So just put a switch over here, and I can run this up, and it goes to the battery somewhere nearby. And so there we go. So if I close this switch, close the switch, I have electrical continuity then, comes through here, comes along here, goes down the coil, finds its way to ground, back that way. Actually it goes the other way, but I told you it works easier this way. This creates an electromagnetic force which pulls this down, which causes the current to then flow through here to the motor and make the motor run. So that's how a solenoid works. Now, again, if I want to put a light over here to see when the motor's running, does that work?
No.
It does not work. You got to figure out another way to do it. So, all right, so, huh?
Could you put it after the motor?
Nope, because think about it. If I put it right here, in reality, the current's really flowing this way. And so if it's in that line, it is not going to work. So I'm going to leave you to figure out the rest of it. Yeah, I know.
That's what they do music for.
That's what you're going to be doing. It's your project. All right, but I need you to remember that most things are not run in series. The only time you're going to do something in series is the components that actually operate something. I'll do it one more time. So if in reality, off the battery, you have a bus. And honestly, in most planes, it's just a thin strip of aluminum. And off of the bus, you tie the circuit breakers right off that bus. So there'll be a whole row of them like that, circuit breakers. And then from the circuit breakers, you'd usually have a very short piece of wire, very short, going to the switch. And the switch is usually just, I don't know, an inch or so away. So that wire is only about an inch, and it goes to the switch. And then from there, you would control your components. Then it'll go out to, out to the wing, and give yourself a landing light or, whatever you have. So you have the bus bar, and then your circuit breakers. And that's how it really looks in an airplane. So you can see what is in series? Well, in series, I have a circuit breaker. And by the way, circuit breaker, and I'll write this stuff down when we get to this in weeks ahead, when it's important and on your test. The circuit breaker is in series with the switch, which is in series with the load, but nothing else is in series with it. I can't run. So on an aircraft, you have wingtip lights and a tail light, 3 nav lights, right? So you have red, green, and white. Well, you're not going to run the red and then the green and then the white in series, because then if one goes out, they all go out. What's that?
If one goes on, the other one. If one goes on, they all go on.
Yeah, you don't want them in series. One goes out, they all go out. So what way it would be done, if this is my nav light switch right here, my nav lights, I want the nav lights on, it's going to go out this way to this light, and then it's going to parallel out to this light. Another one going out here to this light. So you can see they're all parallel to each other. They're all tied into this one spot, but they are not in series with each other. They're all in parallel. It just doesn't look like it because, well, maybe I could have drawn it just a little bit better to make that point better. So let's do it nicer. So this one comes up to there, up to there. That is in fact parallel.
So they just all have the same starting point, basically?
Yes, but they're still in parallel because I can lose this one and these two are going to work down here, right?
Yeah.
Okay, I can lose this one. I'm still going to have my tail light. Now I lost all three. So that means you're not flying at night. Yeah, that's all I got to do. I can fix it. That's all right. I'll fix it. Yeah. All right. So remember that. Very few things in an aircraft. You just don't run components together in a series unless you want them to all to fail. I guess inside the cockpit, if I wanted to put a little light that said that my wingtip light is on, I could run it in series. If this one goes out, that one goes out. Now I know. All right, so parallel circuits. Parallel circuits. That's why I want parallel circuits. Because
Is this still Kirchhoff's law?
it will be in a second. All right, so parallel circuits, what are we going to say? Well, we still have some of the same requirements. Well, we need a power source. What is the power source in an aircraft?
Battery. The engine.
Okay, I've got the battery,
Generator.
the generator. Generator can be engine driven, off the main engines, off an auxiliary power unit. So generator, and by generator, so we have to be careful because sometimes I'll use generators like an overarching thing. It's like whatever's charging the battery. But if I want to get specific, some airplanes really do have a generator and some have an alternator. Just like old cars used to have generators. Okay, same thing. Old airplanes had generators and newer airplanes have alternators.
What's the difference?
Big difference. So, like for example, I used to fly in a Cessna 140, and it had a generator. And generators have what we call a high coming in speed, which means you got to spin them pretty fast before they work. So you take off and fly at night, and you turn on the landing light and the nav lights, landing light, and the taxi light. So they're just like headlights, but it's old timey stuff, not LED. And you watch the ammeter go to a discharge. So he's sucking from the battery now. I can't even keep up because you pull the power back. You add the power and you watch the ammeter go 0 and then start charging the battery and the lights get a little brighter. Pull back on the power and they go the other way. So Volkswagens, right?
Yep.
Okay. So generators, you have to have high RPM for them to work. And a generator converts AC into DC mechanically, while an alternator changes AC into DC electrically with diodes. And they spin much faster and they don't have that problem. We'll get into that in like 6 weeks from now. So power source, conductors. It's a power source. Yeah, we had batteries, generators, alternators. You can have wind-driven generators, conductors, a load. A load and 2 or more paths. 2 or more paths for current to flow. Got to have 2 or more. All right, so let's talk about old Mr. Kirchhoff and his laws, because they're different for parallel circuits. So Kirchhoff.
Okay.
Huh? Laws. I believe so. All right, voltage. Voltage. He says the voltage across any branch is equal to the voltage across all of the other branches. Is equal to the voltage across all of the other voltages, branches. I kind of don't like that because it could imply something else, but I do like this. Voltage total is equal to the voltage across 1, which is equal to the voltage across 2, which is equal to the voltage across 3, on and on and on. Current. So this one right here we just talked about, that's kind of like current in a series, isn't it? Okay, so current in a parallel is I total is equal to the current through 1 plus the current through 2 plus the current through 3, on and on and on. So that's easy. It's just the backwards from a series circuit. But where it gets really different is when we talk about resistors. And that can get really complicated or really easy. So how about we just do it real easy? So we'll talk about resistance. Resistance. When resistors or loads are connected in parallel, the total resistance of the circuit decreases. So in other words, I've got two resistors. I got a 20 ohm and a 20 ohm. How do I make that less resistance? Add another 20 ohm. Add more resistance. It will actually decrease the resistance of the circuit. And I'll kind of show you why, or at least talk about why. So we got that. See, this is very important. And a way to always check yourself. The total resistance in a parallel circuit is always less than the smallest resistor in the circuit. So in other words, if I've got a 1,000 ohm, a 2,000 ohm, a 4,000 ohm, a 5,000 ohm, a 6,000 ohm, and a 1 ohm resistor, my total resistance is going to be less than 1. You do that all day, right?
Yep.
Okay. So, and that's just a great check for you to look at when you're doing these circuits and you're looking at stuff. Well, just take a look at what you got. That's what I do when I check you guys. I was like, okay, well, the smallest one right there is a 10, so it's got to be less than 10. I look at your sheet, it's like 60. I'm like, well, you made a mistake. They're like, well, how do you do that so fast? That's all I'm doing. It's not.
So like we're like computing it and we realize that we have a higher resistance, our total resistance is higher than our lowest resistor, then
You made a mistake.
start from square one.
Start again. All right. Yes.
So it's always less, right? It'll never be the same as the lowest resistor?
It can get really close,
Okay.
but technically it's less. Like if it really is 10, it can be 9.99. Just depends on what the other resistors are. Of course, and this kind of goes back to Kirchhoff's laws with current flow. The amount of current passing through each resistor, that's what I'm going to write next, current passing through each resistor will vary according to its didn't mean to hit that button. According to its individual resistance. Its individual resistance. Okay, so let me talk about the formulas for finding the total resistance. There are several. And I could tell you each and every one of them, but to me, it's easier to throw them all out and pick one that works for all resistors all the time. So that's what I do. So if you want to, there is one in the book, like it's R, if there's two resistors, it's R1 times R2 divided by R1 plus 2. I just hate all that. Then there's another one if there's multiple, but they're the same. Like resistors is R total equals the resistance divided by the number of them. See, and then there's another one. So let's just keep it simple, right? And if I could teach you one, and this is the one I love, it's 1 over R1 plus 1 over R2 plus 1 over R3, and all of that with 1 over is R total. So R total is 1 over R1 plus 1 over R2 plus 1 over R3. Now that sounds a little complicated, but when you actually break it down to what you're doing, it's quite simple. So for example, let's make a couple of resistors here. We'll do 3 of them. And we'll say this is 10 ohms, 20 ohms, and 30 ohms. Well, first of all, the answer is going to be less than 10. Okay, so on my calculator, I don't have it up. So for you with the tan colored calculators, you're actually looking for a 1 over x key. And if you have the blue calculator, it is right above the 7. You have x minus 1. Now, I will often say 1 over x. It's just what I'm used to. I say it, but x minus 1 is the same thing. So I got to move over and get some more real estate over here. And go back up. So we had 10, 20, and 30, right? Yeah. So on my calculator, I'm going to hit 10, and then that key, whatever you happen to have. X minus 1 or the 1 over x key. Okay? Plus 20, x minus 1. I'll try and say it that way. Plus 30, x minus 1 equals, and you're going to get a number. That number is 10 x minus 1 plus 20 x minus 1 plus 30 x minus 1 equals, and it just happens to be here, 0.1833 repeating. Does everybody have that? Huh?
Does this calculator not have a button like that?
X over 1. 1 over x, I mean. Is it? Right there. Right above the EE.
Thank you.
Okay, that's not the answer, even though 1.833 definitely is less than 10. Now you have to hit the x minus 1 and then equals again. X minus 1 equals, and you will get 5.45. If you got that, you did great. If you didn't, we messed up. So that is the formula that works for all resistors.
I did what you did, and I didn't get any of those numbers.
Then you didn't do it right. Let me see if your calculator's broken.
Is it on?
All right, 10, 1 over x, plus 20, 1 over x, plus 30, 1 over x, equals 1.83333, 1 over x, 5.4.
You said turn on.
Just had to turn it on.
Or I have the same
Your
problem.
counseling bill is going up.
Yeah. Is everybody with me on that? Everybody's okay. I'm looking around, looking for somebody going, nope, I'm lost. They'll say I never have any idea what's going on because she pulls her mask all the way up and her hat all the way down, and there's two little, like a suit of armor there. She could be asleep and I would never know it. You're not though, right? Okay. So it doesn't get any more difficult than that. I could put 2 resistors or 100. Now what if I only have 1 resistor? What formula are you going to use?
Series.
No, you just write it down. It's just one. It's a trick question. What's the formula for finding a single resistor? I don't know the formula for finding a single resistor. Okay. So that's the way I do it. Now, if you don't want to do it that way, I don't have a problem with that. There is, and this can make things very difficult, there is a formula for when one resistor is missing. Okay, and it's kind of complicated how you would work it, but I'm going to tell you this, just to keep it very simple. On the FAA test, they would do something like that and say you have 3 resistors in parallel. One of them is a 10, one of them is a 20. What is the missing resistor? Answer A, B, and C. Well, answer A is 11 ohms. Answer B is 5.5 ohms. And answer C is 3 ohms. Which one is it?
11.
No.
Okay.
Either B or C.
You know it can't be A because it has to be smaller than the smallest resistor. And if this is smaller, that's even more wrong. Like if this is 5, that's even more wrong. All right, so I'm left with these two going, well, that would make sense. All you got to do is do 10, 1 over x, plus 20, 1 over x, plus 5.5, 1 over x, equals 1 over x, and then C. Does that make sense? The question I had was, yeah, what is the missing one?
Well,
What other
I'm sorry, I
value
kind of
would
messed
you
that
compare that against? Yeah.
I'm sorry, I kind of messed that up a little bit. So let me just do that one more time. All right, so you have 3, sorry, 3 resistors in parallel, a 10, a 20, and an unknown whose total resistance equals 5.5. Okay, what is the missing resistor? Is it 10? Is it 30? Is it 50 ohms? Okay. Well, there is a formula that I could teach you to mathematically figure this out. But you'd have to remember that formula, which you're not. Can you remember the resistor formula that I just taught you?
Yeah.
You only have to try it 3 times. Worst case scenario. So you'd go 10 1 over x plus 10 1 over x plus 20 1 over x equals 1 over x. What's that answer?
That's one of the 30. You give it 5.4
Is anybody doing that?
or something.
10, 10, and 20. What does that come up with?
0.25.
How much?
0.25.
0.25 ohms. Anybody agree or disagree?
The total was 4.
4. Okay, so it's 10, 10, and 20 is 4 ohms. Okay. Well, that's not it. Let's try 10, 20, and 30. What do we get? 5.45. Well, that sounds an awful lot like 5.5. So the answer is B. How long did that take us?
Too long.
You see my point, though?
Yeah.
There's only like one FAA question that asks that. So probably the time it took me to explain that, I could have just told you the formula. But sometimes you just, I want to find the easiest path through that you'll always get it right. Rather than looking at that going, shoot, man, I'm never going to remember that formula. So, well, that's one I'll get wrong, you know.
Isn't it with the resistors, like they don't, you'll round to the nearest whole number? Right? So then it would be really like 5.5 or 5, then it'd be like a 6 ohm.
It could be anything on the FAA test. They can make up any number they want.
Okay. I mean, but that would just be like with FA, or is that just like in broad, they just round to the nearest whole number?
No, they don't. No, you guys, I'm
No?
looking around. You got your resistors. What are you using? You were using 5.6 or something today? Yeah.
Oh, okay.
Yeah, all different kinds. But you see my point? Sometimes just take the easy path, you trial and error. You only have to try it 3 times to get the answer due. We only have to do it twice because of the way I wrote it. So I don't have to go through the whole example and worry about you freaking out, because hopefully that made sense to you. And you're like, oh, I can do that. I can do trial and error 2 to 3 times. 1 to 3 times, actually. So, all right, let's see how well you can do at this. So I have two resistors. I figured out I need to start writing these smaller and making this bigger. Oops. Yeah, that's not going to work. All right. I of 1 and R of 1, and then E of 2 and I of 2 and R sub 2. All right, and then I will give you, let's see, what am I giving? So we'll go 12 volts, 6 ohms, and 4 ohms. Boom! Mark, set, go. As soon as Hannah looks up, we're gonna do them, because you guys decided she's the pace car, and she's almost done. Ready? Okay. Just like the other one, you're going to look for 2 out of the 3 things here. Of course, we can always put P down here, but I'm trying to save time. Save time, SeaWorld. Yes, I was see. So, what's the one thing that I can... Well, I can complete 2 things on this one real easy. What are they? Yes.
You have your 12 volts for each branch.
12 volts, 12 volts. Don't forget that. It's the same now. Voltage is the same. And then
You can solve for RT.
RT, which is going to be less than 4.
2.4 ohms.
2.4 ohms. And now solve for I, which is just E, I, and R. So 5 amps.
2 amps.
2 amps.
3 amps.
3 amps. All right. Why is it that way? Now, if we think about it, if I put a voltmeter over here across the battery, I'm going to get 12 volts. Well, if I put it right here, that's the same thing, right? That's 12 volts. And also, if I put it here, that's the same thing. If I put it here, that's the same thing as I have right before it, which is the same thing that's here, which is the same thing that's here. So it's going to be 12, 12, 12 all the way across. But if we look at the amps, amps are going to be different in that we can go the right way. We can start this way, and amps are going to flow through here. And how many amps flow through here at this spot?
5 amps.
All of them. So 5 amps. And then it's going to come to here, and the amps, the flow of the electrons, because it's really a flow. It's a number of electrons that can actually be counted. Some of them are going to go this way, and some of them are going to go that way. Well, the number that goes this way just happens to be 3, and the number that goes this way just happens to be 2. So 3 are going to go around this way, take the long way around. You got 2 coming up here, and they're both going to join right here and come back, and that's going to measure 5 going back in. Hopefully that made sense. All right, what happens if, change this up a little bit, not by much. What if I double the voltage? Oh, it's break time, so take a break if you want, work on that.